This example involves a quadratic expression, and we're told to find the domain of a function f of x equals 1 over 1 minus x squared. So again, we've already established the definition of a domain. We know that it is the set of values that x can take on to produce a defined value or outcome for f of x. And from our previous lectures, we know that division by zero is undefined. So essentially, what we're being asked to do here is to find the domain of x. In other words, find the set of solutions or the set of values that x can take on to make this equation true, whilst also making sure that this equation is not undefined. So essentially, what you would need to do is to find the factors of this denominator, 1 minus x squared. And if you remember our lessons on factors, fundamentally, this is a quadratic expression. And so we know that it takes on the functional form or a generic form expressed as ax squared plus bx plus c, right? But if you remember our lesson on quadratic equations, we know that our bx term is missing here, which means that our factors, or the factors of this expression, are such that when we do our FOIL multiplication, we need to be subtracting the inner portion of our expression so that our bx term is 0. I know the book jumped right to the factors here, so if you need more clarity on any of the steps that help you arrive at the factors shown in the second part of the solution, please revisit the lecture on factors where we covered this topic extensively and in detail. So for this particular expression, the domain is all real numbers on the x-axis that do not include this solution set. In other words, the domain is all real numbers that do not include positive 1 or negative 1 strictly on the x-axis. And I thought this example would be almost impossible to understand without visualization. So I grabbed this graphic from Socratic.org, where the same example is available with the visualization of what's happening with this function. A quick sidebar, I should point out that this graph of the solution is not in the book, okay? But this visualization just shows you that if you were to draw this function, so remember when we started here at the beginning of the lesson, we discussed that there are two methods or two approaches to finding the solution of a system of equations, right? The first is by graphing the equations and then figuring out where they intersect, where your graphs intersect. And the intersection point would be your solution. And then the second method was through substitution, which we did here. So in this example, if you were to graph this quadratic function that we've been given, it would look like this graph that's illustrated for us here by Socratic.org. And this graph is simply letting you know that at negative 1, so let me zoom in, you can see that this function does not touch the x-axis at x equals negative 1 and at x equals positive 1. Instead, the function actually breaks apart and continues into perpetuity along the y-axis. So if you were to draw a vertical line at x equals negative 1 and a vertical line at x equals positive 1, you would note the behavior of this function along the y-axis into positive and negative infinity on the y. And you would also notice that this function never touches the x-axis at x equals 1 and at x equals negative 1. And that's because if we were to plug in either negative 1 or positive 1 into our quadratic equation, so let's start with negative 1. If we were to plug in negative 1 in the denominator of our quadratic equation, replacing x squared with negative 1, negative 1 squared is 1. 1 minus 1 is 0. So this function is undefined at x equals negative 1 because division by 0 is undefined. So it essentially has no solution at x equals negative 1, which is what is illustrated on the graph here. The graph itself, in its entirety, represents all the possible solutions for our function. And we can see here that when x is negative 1, the function is undefined, and we've just proved that by plugging negative 1 into the quadratic equation. And because the function is undefined at negative 1, the graph depicts that by showing no contact with x equals negative 1 on the number line, right? And so -1 is not part of the domain of this function. The same thing happens when x equals +1. If we look at the graph of this function, you see that this particular set of solutions, or this graph of this expression, never touches the x-axis at x equals +1. And on the y-axis, looking at everything above the x-axis, the graphical output, which is the set of solutions for this function, from 0 into positive infinity on the y-axis, okay, we see a U-shaped formation that never touches our imaginary vertical lines at x equals -1 and x equals +1, which are the 2 points of discontinuity in the domain of this function, as we've established earlier. And still looking at the y-axis, from 0 into -infinity, in other words, everything below the x-axis, we see symmetry in the behavior of the function as it dips and skates near both points of discontinuity, again, never touching. It skates along into infinity on both sides, never touching either -1 or +1, the 2 points where this quadratic equation is undefined. That's kind of impossible to see from just looking at the outcome of the third step here, right? But essentially what this question is asking you to identify is the domain of this function. And the domain is fundamentally a set of numbers that you can plug into this particular equation to make it true. In other words, the domain is a set of values that x can take on to produce a defined value of the function, or a defined output. So reiterating, if we plugged in -1 into our quadratic equation, looking at the denominator, -1 squared is 1. 1 minus 1 is 0. 1 divided by 0 is undefined, and so this function would be undefined at -1. In other words, -1 is not a solution for this function. And we see that in the graph. The graph is showing you here that at -1, this function never touches, or there's discontinuity in the behavior of the function at x equals -1. The function essentially skips x equals -1. It continues into infinity along the y-axis, both above and below the y-axis, but never touches the x-axis at this particular point. In other words, along the coordinate axes of this function, we can see that the set of solutions for this function consists of all real numbers on the x-axis except -1 and +1. So said differently, the domain of this function is all real numbers on the x-axis except -1 and +1. If you think of this in terms of, or rather, if you remember our lesson on factors, when we were tasked with looking for the factors of an equation, all we were doing was trying to find a solution for our expression. So essentially, we were trying to find a value of x that would make our entire expression true by producing a corresponding value of y. So if you apply that lesson to what's going on here, we can see, or we can test any value of x that is greater than +1. So if, for example, x equals 5, we could plug 5 into this equation. 5 squared is 25. 1 minus 25 is -24. 1 over -24 is going to be some tiny number, so plugging that into our calculator, we get -0.0416. So over on our coordinate axis, if we were to plot the ordered pair 5, -0.416, we would see that at x equals 5, the corresponding value for y is a tiny negative number, very close to but never touching the x-axis on the right-hand side. Okay, and so you can imagine that this continues for any values greater than +1 onwards into positive infinity, as it's depicted here in the graph. And you can test this out for yourself by selecting random values of x that are close or greater than +1, and you'll find the corresponding value will always give you a tiny value for y, close to but never touching the x-axis. This would be true for any value of x greater than +1. You can also test values for x less than -1. So looking at the left-hand side of the axes, any value that we pick for x that is less than -1 would also yield an output value of y that is minuscule and close to but never touching the x-axis. So if we look at the behavior of this function above the x-axis, the U-shaped graph we see here can be replicated by picking values of x between -1 and 1. So let's say, for example, x is negative 0.9. If we plug negative 0.9 into our equation, negative 0.9 squared is 0.81. 1 minus 0.81 is 0.19. 1 divided by 0.19 is 5.26. And we can see from the graph that when x is 0.9, the corresponding value for y would equal or match the output we just found, which is 5.26. At the origin, when x is 0, going back to our function, in the denominator, 0 squared is 0, 1 minus 0 is 1, 1 divided by 1 is 1, meaning that when x is 0, y equals 1, and we can see that modeled on the graph. Looking at the origin, when x is 0, or there's no movement on the x-axis, we see that the corresponding value for y is exactly positive 1. So this function, this equation, is essentially telling you here that anytime you plug in a number for x, or insert a value for x, you're going to find a corresponding value for y on the coordinate axis. And the only time that you wouldn't find a corresponding value for y is when you plug in the factors of this equation, which are -1 and +1, where, as we established earlier, the function is undefined, and we see that behavior in the graph. We see the function, or the graph, breaks up and has several moving pieces from negative infinity up to -1, and then between -1 and +1, and then beyond +1. At exactly -1 and +1, the function dances around the y-axis, but never touches or has a defined value, or essentially remains undefined. So fundamentally, what we needed to do here with this quadratic equation is that we needed to find the domain, or the set of solutions that make this particular function true. And the solution set, or the set of numbers that make this function true, or that would produce a valid output, essentially contains every number that you can possibly think of on the number line along the x-axis, except -1 and +1. And we determine that simply by finding the factors of the denominator in this quadratic equation. And we found the factors of the denominator because we wanted to determine, or we wanted to know, what numbers we can plug in here so that when we do plot the graph, we can understand its behavior based on its solution set. And after our calculations, we had two factors, meaning that the solution to finding the domain of this function let us know at which points this function produces undefined results. In other words, what number would we plug in here to make this function untrue? Or what number would we plug in such that it would not be included in the visual representation of our quadratic function, or that it would not yield a graphical solution on the coordinate axis? And the factors of this quadratic equation, or this quadratic function, tells us that those numbers are -1 and +1. So if we were to summarize everything that we just covered, we could simply state that, looking at the x-axis, if we were to start from negative infinity up until -1, this function would have an output, or a corresponding y value, that would yield an ordered pair that we can graph, and that graph would look like what we see on the left-hand side of the coordinate axes. At -1, however, the function is undefined because division by 0 is undefined, so the function essentially skips. Same thing happens with +1. Now, between -1 and +1, so pay attention to the portion of the graph above the x-axis, you can see that the function is defined, and you can play with numbers on your calculator here by simply plugging any value between -1 and +1, as we covered earlier. Plugging in any value between -1 and +1 into the original function would yield a corresponding value for y, resulting in an ordered pair that you can plot on the axes. The same is true for any value of x beyond +1. So again, the only time that we would not get an ordered pair, resulting in discontinuity in our function, would be at x equals -1 and x equals +1, because both of these values are not in the domain of the function, which is essentially what step 3 is telling you here. In this particular example, we're asked to find the range of f of x equals x squared. So the first thing that you want to